Networks, or ICON. So this is a center that's been of great interest to the controls faculty here at Purdue for quite some time. Essentially, controls is a cross-cutting discipline, as many of you are well aware, and there's some emphasis on control in various forms across all the schools here at the College of Engineering, and actually even beyond. There's really a need and an interest in having an organization that would bring people together under a common umbrella to be able to build a community, share best practices, host events, have seminars, and in general, tackle large-scale grand challenges. So controls is obviously a theme that we wanted to build a control center around. And as many of these grand challenges pertain to large, complex systems, the goal of optimally designing these systems, operating them efficiently, becomes key. And so optimization ends up being a central pillar. And many of these systems are inherently networked and distributed. You can think about robotic swarms or the power grid, social networks, the Internet of Things, cyber-physical systems. So without network thinking, there are big aspects of these systems that we would be missing. And so networks becomes a third pillar that is heavily integrated. And so that led to this idea of a center focused on innovation in these three themes together holistically. And this arose as an outcome of a great deal of conversation with many faculty across the College of Engineering, and also the department heads and the College of Engineering administration. Shashwat, I'd like to really thank the department heads and the college for all the support and encouragement in getting this started. This is something that I think the faculty are very excited about, and so we want to thank them. And so with that, there's also the ICON website I should mention that many of you are already aware, and that's really meant to be a resource not only for the controls optimization networks faculty, but for the College of Engineering in Purdue at large. You'll see things like courses listed there. So if you have students that are requiring to take a course in optimization networks or control, you could go to that website, take a look at that, right? And so keep an eye on that website for things like that and other useful things. And please do let us know, this is meant to be a community effort, if there are other things that you think would be helpful for us to spotlight there. So with that, I'm going to turn it over to Wayne Chen from the College of Engineering to welcome you all from the college side.
All right, good morning or good afternoon, depends where you are. This is the inaugural, the first distinguished ICON seminar series. As you know, the Purdue Engineering is large in size. So in fact, among the top 10 ranked engineering programs in the country, in US, we are the largest. So this size gives us the potential to have the platform to gather a group of people together to attack these large, complex problems. So we have this natural advantage that we have large groups of people. So this ICON is an excellent example that we gather a group of people that I think in College of Engineering, there are already almost 40 faculty signed up. So that gave us a very nice platform. If you account for this faculty, the researchers, grad students in their groups, that will provide a big platform actually for people to gather to exchange ideas. There's also a platform to exchange with ideas with the prominent researchers outside Purdue, just like this distinguished seminar series purpose for. So as Shreya's mentioned, that there's a need and we have a unique advantage to gather people together to attack the grand challenges in the area. But also it takes effort to establish and maintain such a platform. So I would like to take this opportunity to thank the ICON co-directors, Professor Shashwat Moore and Shreya Sundaram, for their leadership and the effort to serve the community. So now I would like to invite the Professor Dimitri Prolas, the Michael and the Catherine Burke head of ECE School to introduce today's distinguished speaker.
Well, thank you very much. I guess from my side, and on behalf of the School of Electrical and Computer Engineering, I do want to congratulate you for launching ICON. It is incredibly heartwarming to have such wonderful news in the middle of the pandemic. And it's wonderful to be able to focus and talk about something different than COVID. So thank you. What you're doing really is amazingly impactful. I can tell you that through the growth path that the school is moving along right now, we are seeing tremendous interest both from the research and education in the areas that ICON is focusing on. We hired, as you know, some of you know, we hired 15 new faculty members in ECE this year, and many of them are really working on areas that are related to ICON. So this is amazingly impressive to see. So, and also underlines the need for launching such a center. We can also see that from the students' point of view. It was interesting for me to see that from the new cohort of online students that we recruited this year, the area of automatic control, which is a central area within ECE that ICON is related to, is actually the #1 in terms of interest. And these are the students who are coming from industry. These are the students who have working experience and they know what really matters in the real world. So thank you again. It's amazingly exciting to see what you're doing. A special thank you goes to the co-directors, Professors Sundaram and Professor Mu. So you guys are leading something wonderful, and we look forward to seeing the great things that will be accomplished here.
Thank you. Thank you, Dimitri. Thank you, Wen. And morning, everyone. This is Shao Shuanmo. I'm faculty at Purdue ECE and also a co-director for Center of ICON. And first, thank you all for your time to attend our very first event. And ICON carries the mission of integrate classical theories in control optimization networks and recent advance in learning, AI, and big data to address the fundamental challenges especially in autonomous and connected systems. So control is the major part. And it's my honor to actually introduce today's speaker, Professor Stephen Morse from Yale University. So Steve is very unique to Center for ICON from many perspectives. And he's a giant in control theories. And he is also a Purdue ECE alumnus, and he received the OECE award. He was actually also my PhD advisor. So today after his seminar, we also invited Steve to share his perspective about Purdue control in history. And also, of course, I will share some stories working with him. And I'm lucky to have him as my advisor. I believe I also give him a lot of trouble. It's very difficult to supervise some stubborn person like Shao Shuanmo. Okay, so I want to introduce today's speaker. So Professor Stephen Morse received his bachelor degree from Cornell University and then master degree from University of Arizona, and then PhD degree from Purdue University in ECE department. He is a Dudley professor at Yale University. His main research interest is in system control, especially he has done many pioneer works in adaptive control, and also now optimal control, and recently multi-agent systems. So he has received numerous prestigious awards, including the IEEE Control Society Award in 1999, and also the Richard E. Bellman Control Award in 2003. So he's a fellow IEEE, a fellow IFAC, and also a member of National Academy of Engineers in the United States. So please join me to welcome Steve for his technical seminar and also his sharing about history of Purdue control. Welcome, Steve, welcome.
Thank you all, and Xiaoshui, I should announce right at the beginning that your troublemaking ways at Yale are known to the Yale Corporation, and only 2 days ago, they decided to revoke your PhD. I will say more about things in West Lafayette and at Purdue during the years that I was first there at the end of my talk. I should also say that it is very nice to be with you, if only in the ether. I have visited Purdue a number of times over the years, and it's regrettable, of course, that the pandemic got in the way of this visit. So let me begin, if I can make my slides work. Thanks to my to the two co-directors and everyone else. So the title of my talk is Distributed Feedback Control of Linear Multi-Channel Systems. And this is work which is in collaboration with my three recently finished PhD students, Daniel Fulmer, Fengjiao Liu, and Lily Wang. Daniel is now looking for a position in a small startup company somewhere in the West. Fengjiao is doing a postdoc with me at Yale, and Lily Wang is starting a postdoc at Boston University. So I want to begin by formulating the problem that I'm going to be talking about. So this talk is a technical talk, but it is not highly mathematical, so you don't have to worry too much. So this is what I would call the basic distributed control problem. It has a lot of ingredients in the formulation. One starts with what is sometimes called an M-channel linear system. M is an integer, generally greater than 1. And the system is basically just a linear system with some special properties as far as the inputs and outputs are concerned. Each input-output pair is called a channel, and so there are M of these, and it's useful to think of the system being controlled by a set of M agents. So I'll use the word agent freely because it helps with the dialogue. The inputs and outputs are vector valued, and the system is assumed throughout to be jointly controllable, and that means if all the inputs act together, the system is controllable in the usual sense. The system is also assumed to be jointly observable, and these are the algebraic ways of talking about it. So this is a partition matrix of B's, the B's from here, and so this is the usual notion of a controllable pair. And similarly for observability, except we stack the C's rather than lining them up next to each other. So these are standing assumptions, and they're really rather mild, and I think if anybody who doesn't make them is working too hard. So say a little bit about what an agent can do. An agent can just only input UI and can only utilize a vector W of signals which it gets from its neighbors. The specification of who agent I's neighbors are is part of the problem formulation. Let's let script N sub I denote the set of labels of agent I's neighbors, including itself. Neighbor relations are conveniently described by a directed graph, which is called a neighbor graph. So what is a neighbor graph? It's a directed graph of vertices 1 through M, and arcs defined, so there is an arc from vertex J to vertex I whenever agent J is a neighbor of agent I. So a very simple idea. Here's a picture of a typical neighbor graph, and what you notice is that there are self-arcs at all vertices because each agent is taken to be a neighbor of itself. What about this vector W? In the case of distributed control, W, this is a vector of signals which are available to agent I. W consists of its output and the outputs of its neighbors, and a bunch of other signals, vector-valued signals. And these signals should be thought of as part of the state of the controller for each I, for agent I. So this is part of the state, and this is the rest of the state. And the distinguishing feature is that Xi is shared, whereas Zi is not. And so agent I knows the shared substates of its neighbors, or say it gets those by communication. We can contrast this with decentralized control, in which case agent I only knows its own output and nothing else. There's no network involved. And in this case, the ith controller state is just Zi. In either case, by a local control, we mean a linear system into which goes Wi and out of which comes Ui. And this system is going to be of dimension Ni plus N wiggle I, the dimension of these two states. So with this much of a setup, we can state the problem. The problem for a given Ni is to find integers Ni wiggle and an Ni plus N wiggle dimensional linear controller, which exponentially stabilizes the system with a prescribed convergence rate. That's the problem, which to me is the number one problem in distributed control. And surprisingly, it's a problem which has not really been addressed very much in the literature, probably because it appears to be hard. One way to try to solve this problem is to use what I'll call distributed observer-based control. So this is a lot of words. And so the first thing I want to do is to tell you what I mean by observer-based control. And then the next thing I'm going to do is tell you what I mean by distributed observer. And then I'm going to put those two things together to get a distributed observer-based control. So first, just a brief review of centralized observer-based control. So most of you have seen this before. One starts with, we could call it a one-channel linear system, standard linear system. And the first step would be design a state feedback law to endow the closed loop with some desired properties. And F could come from any one of a number of places. It could come from a pole placement algorithm. It could come from a Riccati equation if one is doing linear quadratic optimal control. It could come out of an H infinity problem. It's a very general thing, and I'm not too concerned about that. So the problem with this is that X is not presumed to be known. And so what one does is appeal to the concept due to Herbert Simon from the 1950s called certainty equivalence, which says to replace Fx with an estimate Fx hat. X hat is intended to be an estimate of X, and to treat it as if it's correct even though it may not be. That's what certainty equivalence means. And if you do that, the dynamic of the process changes to this. And the next thing is to write down an equation for an estimator. And this is the typical equation for either an observer or for a Kalman filter. And one chooses the matrix K to give the matrix A plus KC some desirable features. Again, if it's a Kalman filter, using a Riccati equation. So let's proceed one step further and look at the state estimation error. If you do that, it's very easy to see that the state estimation error satisfies a differential equation with no forcing function. And that's really important. Why? Because if we look at the closed loop system in these coordinates, EX coordinates, it has kind of a triangular structure. That means that the closed loop eigenvalues, for example, the disjoint union of the eigenvalues of this matrix and the eigenvalues of this matrix. There are many other properties as well, but this triangular structure is fundamental, is critically important. We're not going to dwell too much on this, but I am going to emphasize one point, which I'll call the cancellation rule, which has to do with where this comes from. The cancellation rule means add to the estimator the same signal which is going into the process. So you see it right there. The reason for doing this is when you do the calculation to compute the differential equation for the state estimation error, these two quantities cancel. That is the effect of that is what I mean by the cancellation rule. This, of course, is all well known, but perhaps this point is not being emphasized, not emphasized enough. And in the case of distributed control, this becomes a big deal. And so I will return to this point later. Next, I would like to talk a little bit about the idea of a distributed observer. So in words, the distributed observer idea is for each agent to build an observer, and possibly with communication between agents, so that each agent is able to get an asymptotically correct estimate of the system state. So surprisingly, even though people have been talking about distributed observers and distributed Kalman filters for, I would say, 20 years, only in the last 4 or 5 years have provably correct distributed observers begun to emerge under reasonably general assumptions. There are many, many open questions. For example, there's still no really solid theory of distributed Kalman filtering, or in fact, there probably never will be. Maybe what one needs to do is to change the concept of a Kalman filter for the distributed case. I don't know, but it's still very much an open area, and even the distributed observers is evolving subject, and there are many observers, 5 or 6 I can think of, with different properties. I'm going to be talking using one in this talk, and all the observers are for the multi-channel system, but I'm first going to talk about the observer with no input. So we're going to assume that U equals 0. Why? Because just about every distributed observer out there assumes that the input is 0, or it is some signal with some very special properties. It goes to 0 or something like that. The problem with having non-zero inputs, I'll point it out a little bit later. So the observer in particular that I will be discussing is this. Don't worry, I'm not going to go into the details of these equations in any depth. I will say that the integer q is picked from the set of integers 1 through m, and it could be any integer. And delta iq is the Kronecker delta, which means if I is not equal to q, the differential equation involves all these terms except for the last one. When I equals q, we get the add-on of this system. So agent I uses, for all agents except the qth agent, use an equation like this, and the qth agent uses an equation like this with this term added and this. The dimension of the states of these subsystems are all n, because each xi is supposed to be an asymptotically correct estimate of x. And the dimension of z turns out for the observer I'm talking about to be m-1, where m is the number of agents. So that's kind of a picture of the observer, and there are a lot of matrices here which one would choose in order to make the observer have some nice properties. But rather than, I'm not going to go into that at all. Let me just find the state estimation errors, just as what I did for the centralized case. And then the dynamics, this gives rise to error equation like this. And the z equation can be written with e's on the right. And if you, and we can also, we call this the error dynamics. So this is, if you look at it, like the centralized case, a system of differential equations which have no forcing function. It's sort of kind of an autonomous system. The idea of this observer was developed by Nuno Martins at the University of Maryland and his student Parks, and they published a paper on this which appeared in the Transactions of Automatic Control in 2017. It's a nice observation. I think one of the more interesting things is that they discovered that in order to make progress with this, they needed to appeal to classical ideas from classical decentralized control, and I will say something about that a little bit later on. A little more recently, it was shown that this particular observer spectrum, really the spectrum of this system, can be freely adjusted or freely assigned, provided the neighbor graph is strongly connected. There are other results, but I think for this talk, that's fine. That's a paper that appeared in the Transactions Automatic Control in 2018. So that's pretty much the story with this distributed observer at this point. So what I want to do now is to look at how one would use an observer like this when there's an input, which is what we need for distributed observer-based control. So when there's an input, instead of having ui equals 0, we're going to have ui equals fix as the first step in the design, and the FIs would cause the process dynamics to take on this form. And just like in the centralized case, the FIs can be determined using pole placement or Riccati equations or H-infinity optimal control. There really is no limitation on how the Fs should be chosen, determined by the fact that this is going to be a distributed problem. So the next step is to note that we can't use X because X is not known to anybody. So we use certainty equivalence and replace X with Xi, where Xi is the state estimate of X generated by local observer I. So this is what Asian I implements. Okay, now we have to worry, and that changes the process dynamics to something like this. So we have to worry about the cancellation rule if we want to end up with an error system that looks like this. And we want that so that we can get this decomposition of the spectrum of spectra which we got in the centralized case. So that says what we should do to make sure the cancellation rule holds is add this term to each of the local observers. This term being the same term that appears here. And that indeed will give error equations that look like this, which is what we want. Unfortunately, we can't do this without violating the rules of the problem, because J can take on values for which X sub J is not a neighbor of Asian I. J ranges from 1 to M. So this won't work. So what do? So you stare at this and you scratch your head, and eventually you say, hey, wait a second, all of the Xi's are supposed to be providing asymptotically correct estimates of X. So if that's the case, why do we have to use Xj here? Why not try using Xi and see what happens? At this point, I want to pause for a second because I know there are students listening to this, and I want to say something about research, because this is an example of how research goes. So when you start trying to do a new piece of research, generally you start with what you know, and then you have to jump off into the darkness and guess, maybe using a heuristic or intuition or something. You guess that, say, hey, maybe this idea will work. That's part of the creativity of doing research. If you're not willing to do that, you shouldn't be doing research. And if you are willing to do that, then you can't stop there. You have to make sure that your idea makes sense. If this happens to be an experimental idea, you run an experiment. If you're developing an algorithm, sometimes you can justify that by just running simulations. Or, as in the case here, you try to justify the idea by doing an analysis and actually proving that the idea works. So I just emphasize that as an important component of doing creative research. Okay, so what happens if you add this term? That's going to affect the structure of these equations. And in fact, what it does is it introduces this term. So you notice that the error equations are still defined in unforced dynamical systems. So at least we retain roughly speaking, the triangular property once we change the equations for the process to this. And here I've used these equations to get to this. So the spectrum this is a constant coefficient linear system. Its spectrum, together with the spectrum of this matrix, will determine the spectrum of the closed loop system, just like in the centralized case. So what we really want to do is say something about the spectrum of this matrix. Now, the theory which was developed up till recently didn't have this term. So what to do? What to do? What do we say about this error dynamics? Well, it turns out that all is well. What one can say is this, and this is the theorem. says, no matter what the FI are, the spectrum of this observer's aerodynamics can be freely assigned, provided the neighbor graph is strongly connected. This particular fact is proved in a paper which has recently been submitted for a publication in the IEEE Transactions in Automatic Control. And there's various generalizations of this without making the strong connectivity assumption. So what are the implications of this, which maybe are more important than the theorem itself? The implication is that any jointly controllable, jointly observable, multi-channel linear system with a strongly connected neighbor graph can be exponentially stabilized with arbitrary fast convergence using a time-invariant distributed control. And the way this was established was with an observer-based distributed control. Let me now remind you of what the distributed control problem was again. And the reason I want to do that is because there might be some people in the audience, and I know there's certainly some people in the world who are going to be a little uneasy with this particular approach to distributed control because it relies on an observer. There was, for example, a paper written by John Doyle in the late 1970s, which pointed out that the use of observers can be problematic. It can introduce robustness issues. And so there are people who like to not do things quite using observers. And so with that in mind, we asked this question: are there ways to address the problem not necessarily using an observer? Now, I'm not going to answer that question completely because that's a big question with many dimensions to it. What I am going to do is to sketch some of the ideas that really need to be respected if one tries to answer this question, in the hopes that some other people may come along and contribute to this problem and come up with better ways to control the system than with the distributed observer-based approach mentioned here. So the first thing I want to do is talk about something I'll call the extended system. This is a very, very simple-minded idea. So the first step is, let's assume that each agent introduces a bank of integrators of dimension ni. And once that's done, since each agent knows its own, the bank of integrators are going to be part of the controller that agent I implements. And so agent I certainly knows xi. So we should take what it knew before, namely this, and add to it xi. So xi is also shared with across the network. And similarly, let's extend the definition of ui to include vi, because agent I can control vi. So we have an extended input, an extended input, an extended output, and we now have a system consisting of the process and all of these integrator banks, one for each agent. This defines what I'll call the extended system. And one can think of trying to control the extended system with local controllers whose inputs are the yi bars and the outputs are the ui bars. And the problem then I want to talk about, for given ni, fine integers, ni wiggle it, and ni wiggle dimensional linear controllers, which exponentially stabilize the extended system with a prescribed convergence rate. If you haven't seen this before, let me assure you that the problem posed in this way is identical to the problem posed in this way. It's just set up a little bit differently to make it easier to understand what the problem is. There's absolutely no difference at all. This kind of trick of building state space extension has been used before. I used it with marijuana long ago when we looked at the problem of non-interacting control with dynamic compensation. It's a very, very simple-minded idea. Okay, so the state of the extended system would be the state of the process and the state of the banks of integrators. And it would just be a system that looks like this. Its output is yi bar and the inputs are ui bar. No big deal. And notice that the control, and the controls would look like this. If you stare at this for a second, you say this actually begins to look like a specially structured decentralized control problem because the network has already been taken into account. So if you want to make progress with the problem, so you at least should be familiar with the basic results from decentralized control. So I want to review some of these. So I'm going to do this for an M-channel linear system. So this is the classical decentralized control problem, and this is a review. So Asian I tries to build a linear controller whose input is yi and output is ui, and then apply it to this system. And the problem is to devise local controllers, one for each agent, which endow the resulting closed-loop system with prescribed properties such as stability. That's the problem. That's the basic decentralized control problem that was studied in the 1970s, actually. So there's a classical result which says this. There is a uniquely determined set of eigenvalues called the fixed spectrum, which is a subset of the closed-loop system spectrum, no matter what controller is used, as long as it's time-invariant linear. This is a result due to Shihao Wang and Ted Davison going way back the early 70s. I want to emphasize that as soon as you see fixed eigenvalues, probably think about what happens if you have a centralized system which is not controllable or not observable, so you get some fixed eigenvalues. And this is not the same thing. As a matter of fact, because the system is assumed to be jointly controllable and jointly observable. This is much more complicated, and even to this day, an intuitive understanding of what the fixed eigenvalues are does not exist, in my opinion. The ways to test for fixed eigenvalues, but intuitive understanding, like there is in a centralized case, does not exist. It's quite complicated. So let me mention a few more results. This fixed spectrum is a critical one. There's something called the system transfer graph, which is a directed graph on M vertices with an arc from vertex J to vertex I, whenever the input, whether the transfer function from channel input J to channel output I is non-zero. Then one can state some results. These are also classical. It's a merging of various classical results. Suppose the system's transfer graph is strongly connected. Then the closed loop system spectrum can be freely assigned with decentralized control if and only if for each subset of the set of integers 1 through m, the rank of this matrix, this is called a pencil or singular pencil, the rank of this matrix is greater than or equal to n for all complex numbers s. S appears here, where p bar is the complement of p in the set of integers 1 through m, and c bar and b bar are appropriately defined. Sometime, if you look in the literature, sometimes you'll see for each p, p bar b, an a called a complementary subsystem. So this is a important result. I also mentioned that lambda is a fixed eigenvalue of the system, if and only if this equation fails to hold for some value of lambda and some subset of p. So these are the critical results from decentralized control, which apply to the problem we're looking at now. This fixed characterization of eigenvalues holds even if the system transfer graph is not strongly connected. This characterization is, by the way, is due to Clements and Brian Anderson. I forget Clements' first name. My wife just sent a text message and you might have heard the ding. Okay, so we'll go forward. What did I just do? Okay. Okay, so here's the distributed control problem again. And we have those tools in our pocket. And we're trying to find a controller which does nice things to the extended system. because that is solving the distributed control problem. So what do we know? We need something called the rank deficit, which is the difference between the dimension of the system and the minimum rank of this matrix pencil as P ranges over all subsets and S ranges over the spectrum of A. This particular number is always greater than or equal to 0 because one possible choice of P is when P is equal to this whole set, in which case this is the empty set, and we just have a pencil with A and all the B's, and we know the rank of that is N. So the minimum rank of this cannot exceed N, and therefore delta must be greater than or equal to 0. So here's a theorem. Suppose the neighbor graph is strongly connected. If all of the dimensions of the shared states are greater than or equal to delta, then the extended system has no fixed eigenvalues. So what does that mean? If in addition the inequalities are all strict, then the closed loop spectrum of the original system can be freely assigned with distributed control. Turn my iPhone off because my wife's message, and maybe there's another way to deal with it. Okay, I got it. So what this says is gives conditions under which one can adjust the spectrum and without any statements about observers. And to me, this is a starting point for new research. These bounds are not necessarily the best, so there's research to be done there. The preceding conditions hold whether or not the measured outputs are shared across the network, which is kind of an interesting observation. So you don't get anything by sharing the measured outputs. The above statements does not depend on strong connectivity of the original transfer graph. Examples show that if all the Ni equals 0, which means if there are no shared states and the only measured outputs are shared across the network, it's not necessarily possible to stabilize with distributed control, even if the neighbor graph is strongly connected. A little bit of a surprising fact. The above conditions are not sufficient for spectrum assignability if the neighbor graph is not strongly connected. So just a bunch of facts. So let me go next to talk about an application of the ideas that we have just discussed. I'll call this distributed multi-agent set point control. So again, one starts with a M-channel jointly observable, jointly controllable linear system. And the objective is to construct a distributed control system which enables each agent to independently and precisely set its output yi to a desired constant reference input ri. So it's kind of like a decoupling problem. Each agent can independently do this, except it's a distributed decoupling problem. So the way, a way to do this is to introduce integral control, one of the greatest ideas in all of feedback control, in my opinion. So one introduces an integrate. Oh, I should have mentioned that the y's are scalars. I went too fast through this point in order for this to make sense. In this particular application, let's assume the y's are scalars. So one forms the error between a y and what the set point value we'd like y to take on, and that error then drives an integrator. Then the next step is to combine these integrators with the original process. So you do the combined state would look like this. It would be the states due to the integrators and the state of the process. One defines an extended output because agent I not only knows yi, he knows wi. And we're going to have an input due to the constant reference signals. And if you do all this and write down the state equations, you get a system that looks like this. So first point I want to make is that's easy. These are the matrices that are involved. I don't think this is particularly important. But there they are, where this is ith unit row vector. Worry not about them. What is important are the controllability and observability of the system. So this system is jointly observable, and that's not surprising because it was observable before we added the integrators, and the integrators are added in such a way that agent I can observe its state. So it's not surprising one doesn't lose joint observability. But joint controllability is a little more tricky. One has a condition that must be satisfied, and this is the condition that has to hold. And to demystify this, let me just say that this condition means that the transmission zeros of the transfer matrix of the original system cannot have any zeros at s equals 0. And that is not surprising because we're using integral control. Even in the centralized case, if you have a single input, single output linear system to which you want to apply integral control, if the system has a 0, the transfer function has a 0 at 0, that's going to cancel the pole due to the integrator and cause problems. And so when you do integral control, you can't have that. And the same kind of thing emerges in the decentralized case. And the idea of transmission zeros is part of a linear multivariable control theory. So how do we actually, assuming these conditions hold, how do we actually construct solve the problem? So the first step is to construct a stabilizing observer-based distributed control for the unforced system. So this R is not there. And we know how to do that because we have joint observability, joint controllability, and strong connectivity. Having accomplished that, the control is then, without a reference input, the control is then actually applied to the system with a reference input. And you can say, hey, what happens if you do that? And the answer is that it works because of integral control, even though the limits to which the M integrator, M state estimator errors converge are not necessarily 0. What is true is that all signals in any stable, time-invariant and linear system with constant external disturbances all converge to finite constants. That's well known. Thus, since the output of each integrator so converges, the input to each integrator must converge, so that if the WIs are all converging to constant values, then the thing forcing the integrators must converge to 0, and we've got a solution to our problem. That's the beauty of integral control. So it's very simple to do this, and it's just an application of the idea of the distributed control idea. The last thing I want to talk about, which is really a topic which is still very much in a state of development, is transmission delays. It's not common. There hasn't been much work on studying the effect of transmission delays on distributed control, distributed estimation. Now, if we're going to talk about transmission delays, you can either be a hero first time around and do this for continuous dynamics, in which case you're faced with delay differential equations. It's not the end of the world, but delay differential equations introduce their own complexities, and there's enough complexity without introducing the delay differential equation. So the problem that I'm going to talk about evolves in discrete time, where we can avoid that complexity by using lifting. So the comments that I'm going to make are for a multi-channel linear system evolving in discrete time, perhaps from a sample data system. So in this case, we're going to consider first open loop dynamics. This is analogous to the integrators. And then we're going to extend the system. Well, we're not going to extend it yet. We're going to extend the input to take into account the VIs, just like we did in the continuous time case. And what we're going to do is consider controllers of this form, where yi bar is a signal consisting of various quantities. Here, if there were no delays, yi bar would be yi and perhaps the outputs of the neighbors of agent I, which I've not written down here, and the state Asian eyes of this, and as well as the shared states of Asianized neighbors. So this would be directly analogous to what one is doing in continuous time, and the same ideas apply, the same results hold, the analogous results. However, if we're interested in delays, instead of having available the states of Asianized neighbors, we have only available the states of Asianized neighbors at after some delays in transmitting those states across the network. So there are given transmission delays, which we're going to assume are constant and integral value. And what we want to do is control the system in the face of these delays. So to model this system as a standard linear system without delays, one uses lifting. What do I mean by that? First, they need to define what is meant by the follower of an Asian. Asian I is a follower of Asian J, if Asian J is a neighbor of Asian I. Let's let F sub j be the set of labels of the followers of Asian J. And let's let D sub j be the maximum delay over all followers of Asian J. Then one needs to construct lifts. Lift is a very simple-minded system which looks like this, and what the lift is doing is replacing the delayed state by a state variable of a system which has no delays explicitly in it. This is all very commonly used in the discrete time systems. So one has to build a lift for each agent. Once one does that, one gets these formulas, one can replace this with basically the same signal, but with different symbols which don't involve delays. If one does that, then finally one ends up with a system whose what I'm going to call an extended system, whose inputs are these guys, whose outputs are these guys, but this system has not only this dynamics, but it also has the lifts. So when one builds the extended system, one has to take lifts into account. That does present a bit of a problem. So the state of lift Li is this, and the state of the extended system is X, the Xi's coming from here, and the states of the lift. So it's a big state. And just like any other extended system, it is a linear system, which is going to have feedback that looks like this. So one, again, is confronted with a distributed control problem, which really looks like a decentralized control problem. So one worries about fixed eigenvalues. Now, one thing I'll say about this, about what I've just done, which is maybe not obvious initially, if you go through these steps, so what can we say about these delays as far as controllability and observability of the extended system? Well, it's not surprisingly, the introduction of these delays does not affect controllability because Asian I can control Xj, and Xj drives this whole system. So controllability is not really affected. Observability, on the other hand, is. And the effective observability is to introduce fixed eigenvalues of the extended system at zero. The extended system is not jointly observable. So there's some fixed eigenvalues at zero, which come about because of the lifts. So that means that if you try to do the obvious thing and apply the ideas I've talked about before, there are going to be some fixed eigenvalues at zero. Let me just go to results and tell you what the results are. So we need this thing called a rank deficit, which is the minimum of, I've already defined this before. It's the same, this is the same A, B's, and C's as before, the original system. And here's the result. If the neighbor graph is strongly connected and the and the dimensions of the xi's are bigger than the deficit, then the only fixed eigenvalues of the extended system, if any, are at 0. And those fixed eigenvalues come about because of the lifts. Various things to say about this. The first is fixed eigenvalues at 0 do not affect convergence rates in discrete time. They're all at the origin. So the convergence, you can have as many fixed eigenvalues at 0 as you want. They can be repeated eigenvalues. It just does not affect convergence rate because they're at 0. So you could stop at this point and say, okay, I'm done. As long as I choose the dimensions of these states xi large enough, then I'm going to be able to control the system. However, you could go further than this. Let me just make some comments. So with this is the definition of yi that I had on the previous slide. And I'll say it's impossible to avoid fixed eigenvalues at 0, no matter how large the ni are. And that's obvious because of the loss of joint observability. However, all fixed eigenvalues, including those at 0, can be avoided for ni sufficiently large using a different definition of yi. And these states are the outputs of the delays. In other words, these are the, if I go back to the preceding slide, it's the, I guess I don't have this written nicely. These are the fully delayed, these are the states delayed for the maximum amount of time. Oh, I'm sorry, I have it written right there. So you can avoid the fixed eigenvalues at 0, interestingly enough. But doing this requires each agent to hold its state before transmission to follow I just long enough so that at time t, agent I receives this particular state rather than this state. So you have to delay the transmission before you start the transmission by the difference between d sub I and t sub ij, which is not attractive. The other thing, this in turn requires that for each j, lift Lj play the role of a hold, like a sample hold, and be implemented as part of agent J's controller, rather than just part of the description of the system. And while these ideas enable one to eliminate all fixed eigenvalues, they also complicate controller structure and introduce additional delay in the system. Finally, I'll say there are intermediate solutions which are possible. And in my opinion, this particular subject of when to use holds and when not to use holds, the whole subject is in need of more study. There is some development of these ideas in the paper I mentioned before, which has been submitted to the transactions. Let me conclude with a couple of remarks. This presentation has identified certain architectural requirements needed to address the basic distributed control problem for multi-agent systems with and without network transmission delays. While the results presented assume the neighbor graph to be strongly connected, similar results are also known for the case when the neighbor graph is assumed to be only weakly connected. Weakly connected means you replace the arcs or the arrows in the strongly connected graph just with lines, and in which case you have a undirected graph, and if it's connected, then we say that the original directed graph is weakly connected. Although solutions have been described using distributed observers and spectrum assignment, other more attractive solutions, robust, optimal, adaptive solutions remain to be developed. These are challenging issues, vary, especially things like adaptive and optimal. Any such solution will have to use the architecture components defined here. In other words, we're going to have to use, well, they're going to have to use the components that were described. There's clearly a lot of work to be done in this area. And my hope is that this particular work that's been done so far kind of opens the door to a lot more research in this area. Let me go on now to switch topics completely for the fun part of the talk and to talk about, I was spot on, it's 11:01. Let's talk a little bit about control engineering at Purdue in the mid-1960s. I have to admit, in all honesty, I'm a bit uncomfortable about this because I'm admitting to my age, and I don't like doing that. I like to lie. So first, let me just mention what the basic control group in electrical engineering was. I was in the electrical engineering department. The head guy was a guy named Jack Gibson, who wrote a book in the way back then on nonlinear control. The book is still available. He was a reasonably well-known guy. I was a graduate student at the University of Arizona in Tucson, and he came to visit, and he managed to recruit me. So I came up to Purdue, and there was a group, Violet Haas, I know you know who she is because she was a member of the control group. She was a strong promoter of getting women into engineering, and she was very good at it. Her husband, Felix Haas, was the provost, and I believe there's a building at Purdue named after him at this point. So Gibson was my advisor when I first went to Purdue, and he left for another school at some point, and Violet Haas took over and became my advisor till I finished. Another member of the group was Boyd Pearson, who was an assistant professor at Purdue at the time and went on to Rice University, where he filled out his career. Pearson is quite well known in the control community. The connection between him and me at Purdue was that I took linear systems from him, and he taught me linear systems using the book Matrix Algebra or something by Gontmacher. I don't know how many of you have seen that book, but it was a predecessor to the well-known Horn and Johnson books. Gontmacher is actually a very, very good book, but it takes some effort to learn some of what's in it. I particularly remember agonizing with Pearson over elementary divisor theory, but I did learn something, and of course, the only way to learn something is to go through some pain, and I certainly went through a lot of pain at that point. Another person in the group, who I'm sure some of you know, is King Sung Fu, Chaos Fu, who was into pattern recognition. Fu has gone on to great prominence. There is an award by the Pattern Recognition Society. I don't recall exactly what the name is, but it's the Chaos Fu Prize. Another person who you probably don't know, who was part of the group, was Zeno Rakeshis, who eventually went on to Northwestern. He did some work in non-interacting control, which influenced me for work that I did later in my career. And finally, Antti Koivu, who I think stayed at Purdue and must still be around. I think he joined Purdue around the time that I got there. So I got to know him pretty well. I also got to know his younger brother in Finland, who hosted me at a very wonderful event in connection with an IFAC Congress, which was held in Helsinki. In addition to these people, there was one other guy, Sid Sridhar. I couldn't find his picture. He was a very smart fellow, I think interested in stochastic control, who left Purdue to go to Caltech during the time that I was there. Unfortunately, he passed away at a very young age. Two other people in the group were Kashyap, who I think stayed at Purdue. He joined after I got to Purdue, and Digafirito, who also came to Purdue and then left a little bit later on. So this was, roughly speaking, the group of people in control in electrical engineering. I may have forgotten somebody. There was a guy named Johnson Liu who came later on, but I absolutely could not find out any information on him from the internet. So in addition to people in electrical engineering, there were a number of other people in control at Purdue. Perhaps the most Well known of these was Rufus Oldenberger, who is a very well-known control guy in mechanical engineering. I can tell you that I was listening to the dean talk today about your center, and I'm delighted to see that it's cross-departmental lines. Back in the days of Oldenberger and Gibson, there were wars between the departments, and there was no collaboration at all, which was very silly, but that's the way the personalities were at that time in history. So Oldenberger has an award, an ASME award in his name. He's very well known. Another guy back in that area from the math department was Leonard Berkowitz, who I think passed away in the last couple of years. Berkowitz was very much into optimal control, and I'll make reference to him again. He was on my committee. He taught me optimal control. He's a very, very nice, smart guy. Another guy who came to Purdue from industry was Ted Williams, who went to chemical engineering, and I got to know him pretty well. And another one I can remember was Leon Chua, who I think many of you would know. He's going off to Berkeley. He was an assistant professor at Purdue when I got to Purdue. He didn't really do control. He did nonlinear systems. And some of the things that I think made him famous, he may have been talking about while he was at Purdue. He invented a circuit element, if I remember correctly. One other guy I should mention, because of his influence on control, was Julius Tao. Tao actually left Purdue before I got to Purdue, maybe by a year or two. But he was very influential. He went on to the University of Miami and has written many, many textbooks on control, which you could just Google his name, you'll start seeing them. One thing that I think he had to do with, which had to do with West Lafayette, was a Chinese restaurant. So at the time that I was in Lafayette, things were pretty bleak. They were not so good as far as restaurants. In fact, they were horrible. There was on Northwestern Avenue, very close to the electrical engineering building, a Chinese restaurant, which was very good. And I think Tao played a role in bringing that particular restaurant about. In fact, for a while, I thought that he was a co-owner, but maybe I was wrong. The restaurant was good enough so that people from Champaign-Urbana would drive all the way to West Lafayette just to go to the restaurant. So that's where things were in the 1960s. I had a bunch of office mates, some of whom you will know. This guy, probably not, Syed Murtuza, was an office mate who stayed at Purdue, but not the West Lafayette campus. I think he went to a satellite campus. Another guy, Lloyd Jones, who didn't even stay in control. He went to become a minister. The third guy you'll know, George Saritas. George went on to be instrumental in the development of the IEEE Automation and Remote Control, Robotics and Automation Society. And there is an award in his name given by the Robotics and Automation Society. He shared an office with me. And Phil Swain, who was on the Purdue faculty, I believe, until he retired. I don't know who this guy is. And there was one more guy I'll mention who was a student of Berkowitz. He was a mathematician, Tom Banks, who went on to do, among other things, become the editor-in-chief of Siam Journal of Control and Optimization, which some of you may know has been one of the leading top 2 journals in the control field. And I've had ongoing contact with him. Let me talk a little bit about some of the research things that were going on at Purdue during the years that I was there. Absolutely, for sure, the big game was optimal control, the maximum principle. People were beginning to discover it. Dynamic programming due to Bellman, linear quadratic optimal control had been pushed hard by Mike Athens at MIT. Gradient algorithms and quasi-linearization were being proposed to solve the Euler-Lagrange equations, which go with the principle of the maximum principle. So there was a lot of work in this area, and I participated in this as well. Another area of research, maybe less so, but still active, was stability theory, nonlinear stability theory, and Lipuna functions were certainly around at Purdue, and the circle criterion had been developed in the early 1960s by various people, not at Purdue, but it was certainly being studied. Stochastic control was another area of study. Nonlinear control, I think the main tool in nonlinear control was describing functions. There was absolutely no nonlinear geometric control theory. That did not develop until the 1970s. Differential games were very popular back then. In fact, I was studying, I studied differential games. It was part of my doctoral thesis. The name Rufus Isaacs, who was not at Purdue, but he was a big name in differential games. And of course, Kalman filters and observers. Observers had just been invented a year or two earlier, I think, by Dave Leuenberger. Kalman filters were a little bit older. Realization theory, controllability and observability, and things related to that were certainly being studied. And that was also Kalman work, which had actually come originally out of the circuits field. There were applications to space travel, which I was involved in. This was in the 1960s, so it was before the United States, not only before we went to the moon, but before the United States really made much of a presence in space. Trying to remember the story of, I can't remember, there was a story to do with Sputnik, which goes back to 1957, but I can't remember the story. But what I can remember is that when we worked on, there was a group of us at Purdue during my graduate days who worked on something called Model Vehicle Number 2. Model Vehicle Number 2 was a post-Saturn V class vehicle, which was a real big vehicle. And we were concerned with controlling it. It like Saturn V, it had gimbaled engines on the bottom, and you controlled it by swiveling the engines. The thrusts were not under control, they were pre-programmed. And the problems were extremely challenging because of the size of the vehicle. So things like bending frequencies, bending modes became important and became part of the control problems. And so we studied that. This was, Purdue was one of 4 universities in the United States funded by NASA to work on, I believe, Model Vehicle Number 2. Eventually that whole program was scrapped. It had like many programs in the government. Finally, there's the pole placement. And I want to tell a story about pole placement. I actually have a movie, but I'm a little worried about time. How much time do I have a lot of time?
Yeah, we've got essentially until noon, and of course, if people drop out, that's totally fine. But you know, this is essentially why we're here, and please take your time with it.
All right, let me move to the movie. I was debating whether to do this, but I think that I will. Oh, that's not it. Okay, so what does this have to do with broccoli? What does pole placement have to do with broccoli? So here's the answer, and this does have something to do with Purdue. Well, first I should show this movie.
You can't hear sound.
You can hear that?
We couldn't hear that.
Oh, well, that's very unfortunate. That's George Bush Sr. saying, I do not like broccoli. I don't like it since I was a little kid. My mother made me eat broccoli. I'm not going to eat any more broccoli. That's a famous bit. And what does that have to do with the story I'm going to tell? So I've used this in presentations, and what I start by saying is, I don't like optimization. When I was at Purdue, all I studied was optimization. I'm not going to use optimization anymore. And so what does that, just to make people laugh. And what does that have to do with with pole placement. So here's the story. When I was at Purdue, people were kind of fanatical about optimization. I mean, it was excessive. During my stay, some guy came in, this was before a post placement theorem came up. Some guy came in to give a talk on placing the poles of a linear system under state feedback. And his idea was to set this up as an optimization problem. So the problem was to adjust the coefficients of the characteristic polynomial of a plus bf with the entries of the matrix F. And so the entries of the matrix, the characteristic polynomial of a plus bf, of course, determines the eigenvalues. So unfortunately, the coefficients of the characteristic polynomial of a plus bf are nonlinear, actually multilinear functions of the entries of the matrix F. So that if you set up an optimization problem, it's fairly easy to set up such a problem, where if you could find the minimum, you would have a solution to the pole placement problem. But the catch is you can't find the minimum because the optimization problem is highly non-convex. And the reason I mention this story is because it's a perfect example of what I would call very uncreative research. When I got done at Purdue, I went to NASA Research Center in Cambridge, Massachusetts, and Murray Wanham was there, and he had just proved his pole placement theorem. He didn't use any optimization at all. So the message that I'm trying to get across is beware of people who try to convert every problem into an optimization problem. It's not creative, often does nothing. I would be very, very skeptical about that. I'll give you another example, two other examples of problems where people have attempted to set them up as optimization problems and really gotten nowhere. One of them is a matrix completion problem. You have holes in a matrix and you're trying to put the entries in to end up with a positive definite matrix. And so people have studied that as a optimization problem. It's stupid, in my opinion. Another example of such a problem is network localization problems. If you want to do localize, find the positions of a bunch of sensors in the sensor network using localization. The basic problem, because of Pythagoras, is nonlinear. And so to try to deal with it by setting it up as an optimization problem goes nowhere, but people have done that. So those of you who are starting out in your careers, I ask you to think twice before you run off and set things up as an optimization problem. There's more to life than optimization. Okay, I'll go on a little further now. So I mentioned some notable visitors that came to Purdue during the years that I was there. First one was Manfred Thoma. Thoma, you may know, was a very active member of the International Federation of Automatic Control and recently retired recently. And there's an award in his name. And I believe Ming Chow, who was my student, was the inaugural winner of the award, but I'm not sure. But anyway, there's an IFAC award in this guy's name. Thoma was a very nice guy, a very funny guy. He's German, so his English was a bit abrupt. I remember having a conversation with him one day and asked him, he said he was going to go on vacation. I said, where? He said to the West. He was going to visit about 6 or 7 states. I said, how long are you going to, and he's going to drive. How long are you going to take to do that? He said, 2 weeks. And my eyes rolled. If any of you have been in the West know that you can't get very far in 2 weeks visiting 6 or 7 states. Another guy who I think you all know, who visited Purdue in the 1960s, was Rudy Kalman. I won't say anything about him, but I will say that other than the fact that when he visited, I had no idea that he was a celebrity, a big deal. I was just a young graduate student. I have since written an article. It would appeared in the Control System magazine as part of a tribute to Kalman. Appeared a couple of years ago, which you might want to read because I do mention Purdue and that particular incident, and along with a number of funny incidents involving Kalman that I know about. Another guy who visited Purdue back in that time was Lotfi Zada. Zada was just beginning to talk about fuzzy sets, and he gave a talk on that subject at Purdue, which I remember. Another guy who visited many times was Robert Kalaba, who was a colleague of Bellman and well known in his own right in mathematics for optimization, contributions to optimization, and he pushed an idea of called quasi-linearization, which is a computational technique for trying to solve Euler-Lagrange equations, and something that I had a lot to do with when I was at Purdue. Two other guys you may not know, the younger faculty, the younger graduate students may not know. One is called Gamklaritsa and the other one's called Mashenko. Mashenko definitely came to Yale at the invitation of Berkowitz, Len Berkowitz in the math department. Gamklaritsa may also have come, but I can't remember because it was so long ago. And some of you may say, who cares? Who are these guys? Well, you can tell by their names that they're Russian. Remember, they were coming to the United States at a time when relations between the Soviet Union and the United States were not so great. So when they came, like any other Russian visitor, there was always another person from the KVD, from the Russian secret police, who were watching to make sure they didn't escape. But who are these particular guys? This ought to help you figure out who they were. This is the paper, the original paper on the maximum principle. They are the second and third author of the paper, and Pontryagin is the fourth. So they're really a big deal in optimization circles. So let me go on and talk a little bit more about notable Boilermaker who was at Purdue. So I'm not talking about the International Brotherhood of Boilermakers. I'm talking instead about Bob Greasy. Bob Greasy was the quarterback of the Purdue football team, at least during one of the years that I was there, and Purdue went to the Rose Bowl. My comments now are really directed towards the international students about this. I strongly urge you to go to a football game after the pandemic, not because you have to be a great lover of American football, but because it is a happening. It is an experience which I think you will enjoy because it's so unusual. There will be things like tailgate parties before the game, and there will be the behavior of the fans is a little crazy. Everything about the event is unusual, and it's worth going just for the fun of it. Sort of like going to a World Cup soccer game, I guess, a similar kind of thing. So I urge you to do that. Researching this talk, I, of course, was led to this Boilermaker sign by accident. I was not led to it by Googling Boilermakers. I was led to it by Googling locomotives and Purdue. And unfortunately, what I was looking for, I never got, but what I did get was this. And this is where the name Boilermakers, I don't know if it's where it comes from, but it's closely related. This is a steam locomotive given to Purdue. It's called the Schenectady, and it comes from Schenectady, New York, which makes me think it has something to do with General Electric, which was in Schenectady. If you look carefully, you'll notice that it says Purdue University 1890 something. So this goes back quite a few years. And the reason it went to Purdue is because this was an era in which steam engines were really a big deal as far as commerce is concerned. And so people wanted to make sure that they were being operated as efficiently as possible. Purdue had some kind of a steam engine laboratory or something back then. And so Purdue was given this engine to study it to see if they could make it behave better. And through this process, I believe the term Boilermakers emerged. So what led me to this was not trying to find out where the term Boilermaker came from, but rather something a little different. As it turns out, during the years that I was at Purdue, there was a locomotive on campus. Not only was it on campus, it was functioning. So I lived in what used to be called the married student courts, and they were on the corner of State Street and Airport Road. And in order for me to get to the electrical engineering building, I'd walk down State Street and then I'd start walking across the campus. And not too far into that walk, there would be a railroad track. And on that railroad track was a modern locomotive, not an old steam engine like this, and a coal car. And that, I can't remember if the steam engine, if it was a steam, I don't think it was a steam engine. I think it was, when I was there, it was probably a diesel engine. And the role of that particular engine was to carry coal from some location, which I don't know where it was, to the physical plant which generated the heat for the whole university. And I think that was there all the years that I was at Purdue, but I can't remember. And anyway, I know the next time I came to visit, it was gone. So that kind of brings me to the end of my talk, and a little bit of discussion about Purdue. Thanks for listening.
Thank you very much, Steve. Thank you. And especially thank you, for the review of the history of Purdue Control.